Morning.
Have to shut that door. Dr. Stone is just way too loud over there. Let me go ahead and pass this around. It's out of the way. sign in. You're just in time. It's right there. So.
Just in time with the story of my life.
Okay, we're going to go ahead and get started here. Sign-in sheets going around. If you haven't checked it, make sure you do. And we're going to start talking more about Chapter 1 today. And so anybody have any questions on anything we talked about on Monday? I can't remember what I did yesterday, so I have no idea what I did on Monday. So, okay. And if you're in lab this afternoon, we'll be meeting in here at 1 o'clock. Yesterday, it went for about an hour, and it is incredibly boring. I'll just tell you that right now. So, but it does get better. So,
We just rather get it.
oh, you didn't get it? Oh, okay. That's okay. Yeah. Yeah, I believe in being completely honest, and lab this week is incredibly boring. I'll just tell you that right now. So, but it will get better, trust me. So, okay. So let's move on here. If you're in Zoom, you should be able to see the slide that says Chapter 1, Introduction to the Human Body. Thank you. Assuming I haven't muted myself. And I'm going to go ahead and open this screen up and minimize that distraction. Okay, so we had gotten, we talked a little bit on Monday about the differences between anatomy and physiology. Anatomy is function, anatomy is structure, physiology is function. And the compatibility of the two terms, that the function of a structure is in a lot of ways based on what it looks like. You know, I gave you the example of the 4-chambered heart. The 4-chambered heart can pump blood into both the lungs and to the body at the same time because of the way it's designed, with 2 upper chambers and 2 lower chambers. Physiology and anatomy have to work together for us. You know, things work the way things look like they do because that helps them to do their job. And we talked about the different types of anatomy, you know, gross anatomy and microscopic anatomy. We talked about physiology and why we have to study a little chemistry in here and understand pressure and electricity in here too. We also started talking about the terminology a little bit because left, as I said the other day, left and right and up and down can be very confusing terms for us if we don't use them in the correct way. Again, complementary structures and functions are complementary. And then we looked at the organizational levels. You know, from the simplest level of an atom and a molecule, or even an organelle. An organelle is like a tiny organ found inside a cell. The nucleus of a cell. You've all heard the term nucleus, right? You know what a nucleus is. It's the center of the cell. That's an organelle. It's the largest organelle inside the cell. But the organelles all have specialized functions, much like our own organs do in our body. Those are some of the smallest structures that we encounter. And we start putting things together, go up to the size of a cell, to tissues, which is groups of cells, organs, which are groups of tissues, organ systems, where no organ system operates independently of any other one. The heart has to pump blood that is oxygenated. It's oxygen for the lungs. The blood has to be filtered by the kidneys. We have to get rid of the waste products. We have to get energy to pump our blood and move our muscles. We get that from the digestive system. If we get too hot, we radiate extra heat away through our skin. So every system has to work together. No, we can't take one system offline and expect the body to function properly. And then when we put all the organs together, and all the organ systems, we get us. And we had started talking about the different organ systems. I think I got, I think I showed you this slide, didn't I? Yes, I thought so, yeah. It is always amazing to see what people do accidentally or on purpose to themselves. No one accidentally drops a box with 80 and has 87 nails go into their belly. That took some effort to do that. But we're going to see other things that happen, that people survive. Our bodies have an amazing ability to survive a great deal of trauma. I went through this. And okay, so this gets us to, what do we need to live? What are the requirements for life? And we have another one of these great little pyramids here. And to maintain life, and not just to exist. I mean, if you're in a space station, for example, the International Space Station, or maybe you're lucky enough to go up in what's the New Shepard rocket that gives you the suborbital flight where you can go into outer space for 10 minutes or something. Or maybe you work for Elon Musk and you're an astronaut and you resupply the space station. Can you live in space? No, because there's no air there. The temperatures are extreme. There's no food available there. You have to bring everything with you. So it's not enough to have everything available. All these things, the functions, the requirements of human life require more than just, this is like being able to breathe air. We can do that. We can drink water. We can eat food. It's there, the resources are available to us. It's the same as if we were to be in a submarine. You can survive in a submarine as long as the submarine is making its own oxygen, which it does, and there's plenty of food there for you to eat for a while, and you can stay comfortable, and it's air conditioned or it's heated for a while. So, okay, to maintain life, we have to be organized. Things have to function properly. We have to also keep our boundaries. We have to keep things outside our body or let things in. Metabolism is how we burn up our food. Are we responsive? Now, let me get to here we go. Organization. We go from the smallest to the largest. Go from the organelle, to the molecule, to the organelle, to the organism. Now, boundaries, we even though we may like each other and we may like people, our bodies don't like each other. Our bodies don't like people. We keep away from things all the time. Our cells are covered by a membrane that protects them from other cells. Cells don't even like to be crowded. Cells have something known as contact inhibition, where they don't let too many cells grow around each other. It's like, when you're in line somewhere and someone comes up behind you and just gets a little too close, it invades your personal space. We all, who hasn't seen that, or who hasn't experienced that? We have this little magic ring around us that when you get inside that ring, you're too close. Get away from it, So cells are the same way. Cells don't let other cells grow up next to them too close. They have contact inhibition. Our skin protects us from all things around us in the environment. All the pathogens, viruses and bacteria and funguses, sharp objects, chemicals, all sorts of things our skin protects us from. It keeps us separate from our environment. So we try to, we have to keep our boundaries. We don't want to lose all of our water through our skin. We don't want to lose all of our oxygen through our skin or all of our blood. All those are bad. We want to keep things inside our body. We don't want things to penetrate. Now, metabolism, chemical reactions in our bodies. We have two steps in metabolism. One is called catabolism, where we break things down. If you ate something this morning with carbohydrates and proteins or whatever if you ate something at all, then your body is breaking that down right now. A catabolic reaction releases energy. If you drove here, which you probably all did, your vehicle had a catabolic reaction in the engine to take stored energy in the form of fuel, whether it was gasoline or diesel or even electric. The stored energy was converted to mechanical energy. That is, the stored energy was broken down. That's a catabolic reaction. We do that when we eat things. We break down food and we release the energy. But some of that energy then we use to rebuild other molecules. If you eat protein, if you ate an egg this morning for breakfast, the white of the egg is pure protein. Now, our bodies use protein all the time. Our hair, our eye color, our skin color, all of our enzymes in our bodies, some of the proteins in our bodies are extremely strong, and they wrap themselves around our bones to make them even stronger. So we have to use protein all the time. Now, albumin is a great protein if you're a chicken. But what we can do is we can take that albumin and break it down to its individual components and then rebuild it to what we want. And those are called anabolic reactions. So we take proteins and tear them down and rebuild them so we can use them for our own needs. We take carbohydrates. We may eat a donut, and the donut is sugar and starches. It's a carbohydrate because it's starchy and sugary and whatever. And we can take that and break that down to the individual glucose, the individual sugar molecules, and then we can rebuild those sugar molecules and store them in our bodies as a very large molecule called glycogen. Glycogen is the human version of starch. We don't store starch like plants do. Who hasn't eaten a potato at some point, right? Potatoes are starchy.
I like them baked.
Yes, that's I don't think I like them any version I give. I love baked potatoes. So the inside the potato is starch. Okay. Well, our bodies will convert that down to glucose, to sugar, and we'll use some of it for energy, and the rest of it we will store in our liver to use as a larger molecule called glycogen to use again. Because we don't store starch, we store glycogen. Just like plants don't store glycogen, they store starch, but it's the same type of molecule. And we'll talk a lot about that when we get into chemistry. So our metabolic activity consists of both building things up and breaking them down, and it goes on constantly. And of course, if you like visual, this is what happens. Catabolism, large things become little things, and anabolic reactions, little things become big things. In a catabolic reaction, we always release energy. Lighting a match is a catabolic reaction. We are breaking down the larger molecules into smaller ones, and we release energy. But making the match is an anabolic reaction where we store energy in the match, in the chemical. So, or even something even simpler, consider baking a cake. You mix all the ingredients together. This is when my wife always laughs at me when I try to give this analogy. about baking a cake because I always get it mixed up. But you take all the ingredients and you mix them together and you apply heat to it in the oven. And what do you get? You get a cake. If you didn't apply energy to it in the form of heat, what would you have if you just had it all mixed together in a pan? Nothing. You know, you'd have cake batter. Not that there's anything wrong with cake batter. I'll just throw that out there. But you're not going to have a cake. You apply energy to it, and now you have a cake with energy stored in there. So just consider that. Okay. Responsiveness. Do we respond to a stimulus? Do we respond to noises? Hopefully. Do we respond to odors and pressure and touch and pain? Yes. We respond to heat and cold. If there's a loud noise out in the hallway, we're all gonna turn our heads and look in the direction of the hallway. Or if there's a flash of light outside, we'll tend to look towards the window. We respond to stimulus all the time, even when we're asleep. Because just because we're asleep, our ears aren't shut down. We wake up and we hear a noise. You know, some cases, for some of us, it has to be a very loud noise. Others are much more sensitive to noise, or it has to be a certain type of noise. You know, if you're the parent of a small child, you often wake up when that child coughs or sneezes or cries in the middle of the night. And yet you can sleep through the sound of I don't know, someone revving up their motor at 3 o'clock in the morning to see if it works. One of my neighbors likes to make sure his motorcycle works at 3 in the morning. So just in case it didn't work for him. So, and that's okay. So, but I sleep through stuff like that. But when our boys were little, I'd wake up, when I hear a sound. So it's all selective, but we respond to stimulus and we move. We move a lot. It isn't just walking back and forth or taking notes or whatever. It's pumping blood. It's maintaining your body's posture. It's moving fluid through your digestive system and food. It's moving fluid through your urinary system, filling up your bladder. Your bladder is stretching. So all these things are movement involving our muscles. So it isn't just raising your arm around or something like that. And we have 3 different types of muscles. We'll talk about that in lab probably next week. But we have skeletal muscle, ones we control. We have smooth muscle, the ones that line our blood vessels, line our digestive system, line our airway. We don't control those. They act on their own. And then we have cardiac muscle, which is found only in the heart. It operates on its own. There is no outside control in the heart. The heart is a self-starter. So, okay. What else happens to us? Well, we grow from infancy, from one cell to an adult in 20 some years. We change, we differentiate the cells. The concept that we are an undefined ball of cells only holds true for about the first 48 hours after conception. After that, we start differentiating, meaning we start developing into our structures. Consider that 3 weeks after conception, we have a heart in place. It's already beating, and the arms and legs have already started to form. We have a full skeleton in place 6 weeks after conception. We are about the size of a aspirin tablet at that point, and yet we have a full skeleton. So we change drastically. We grow. We grow from one cell to billions of cells. We reach our adult stature. We really don't stop our growing until we're about 23 years old, even though the bulk of our growth occurred probably at some point in puberty. either earlier and later in puberty, but we reach most of our adult stature then. Growth doesn't stop until we're about 23 years old. So we reach our full body stature then. And we have the ability to reproduce, not just sexual reproduction, but replacing worn out cells, because we're always replacing worn out cells. Our cells undergo mitosis. They get damaged, they get worn out. That's what their job is. The cells on our skin, on the surface of our skin, are dead cells that were alive a couple days ago, and they're being shed constantly as they wear off. They're also there to protect us. We have thick layers of dead cells on our skin so that when we bump into things, which we do all the time, we don't get injured. When we were kids and we'd fall down and we'd tear up our knees or tear up our elbows or cut ourselves, like I still cut myself accidentally. So, or my dogs help me out. My dogs like to play a lot and they play rough. And so I always look for the blood afterwards, which anyway, don't wear a white shirt if you play with dogs that play rough. I'll just tell you that from yesterday. So the cells are going to be growing back again and again and again. That's what they do. They're designed to wear away. The cells inside our mouth and the inside surface of our mouth are designed to wear away as we eat things. The wear and tear that we experience. We don't have any damage. You generally don't hurt the inside of your mouth when you're eating something. At the other end of the digestive tract, at the anus, same thing. Lots and lots of cells there to protect us from wear and tear of stuff leaving the body. So we have cells that are constantly replacing themselves and repairing themselves all the time. And then, of course, we get into the whole reproduction, sexual reproduction, which goes on throughout the fertile years, if you will. Your female is capable of ovulating an egg every 28 days for about 30 or 40 years. And males will produce sperm from the onset of puberty till the day they die. Females produce their eggs or release their eggs from the onset of puberty till mid-50s, maybe. So it depends. It's variable in everybody. So, okay, so those are the things that we, that our bodies have to do to survive. Now, to live, we've got to have oxygen. We've got to have air to breathe. We last for about 5 minutes or so without oxygen. Nutrients, we have to have food. We can go for about a month without food. We have to have water. We can go about 3 days without water. Of course, the last day we're sort of in a psychotic break, so we really can't do much about getting water at that point. So it's really only about 2 days before we get into real trouble without water. Body temperature, we have to stay right around 37 degrees C, 98.6, somewhere in there, because our bodies are designed to operate in a very narrow range of temperatures. We don't like to get too hot or too cold. The enzymes, the chemicals in our bodies that control a lot of the reactions, the enzymes are designed to function within very narrow ranges of temperature. They don't like high temperatures or low temperatures. And so we have to maintain a normal body temperature. And we have to have enough air pressure to breathe. It isn't just having oxygen available. We have to have the appropriate amount of air pressure. We're about 1,000 feet above sea level right in here. And the air pressure, I'm not going to get into the physics behind it here. The air pressure here is about 760 millimeters of mercury pressure. That's one of those, Well, that's what they teach us in professor school, to say nerd things like that. So you're really impressed with what we know. So, no, seriously, 760 millimeters of pressure. Okay, that's fine. That lets oxygen. That's enough oxygen. What that means is there are enough oxygen molecules in the air pushing against us. Because that's where the pressure is coming from. We don't feel it. We don't see it. But there's oxygen molecules and nitrogen molecules in the air pushing against us. That's the measured pressure. And that means there's good exchange of oxygen in the lungs. If we go up 10,000 feet in elevation, the air pressure drops to 360. 360. It's 360. It cuts in half. Let's just say 360. Now, it still means that there's oxygen and nitrogen there. Remember, we're breathing a mixture of gases that are 20% oxygen. At 10,000 feet, it's still 20% oxygen, but the amount of oxygen has been cut in half. We can survive at 10,000 feet. We won't like it, but we can survive there. You know, you can, if you've ever been to Colorado, there's a town in Colorado. It's just sort of like the Gatlinburg of Tennessee. Estes Park, Colorado is the gateway to the Rocky Mountain National Park. So it's sort of like, like Gatlinburg does. It's at 10,000 feet. And if you go there, and if you fly into Denver or something and you go up to Estes Park and you've left somewhere like around, if you go from here to Estes Park, you're going to notice that you're not going to have enough air to breathe. If you try, you can walk along and breathe just fine, but if you try to run across the street when the light changes, you'll very quickly discover that that's not a good idea, because there's not enough, your body hasn't acclimated to the lower air pressure yet. Because when the pressure drops, the percentage of oxygen stays the same. There's just less oxygen molecules there. That's what the pressure is all about. At 10,000 feet, there are half as many oxygen molecules as there are at sea level. The ones that are there are still at 20% of what's available, but there's half of it. Now you go up to 20,000 feet. You can't survive unassisted at 20,000 feet. There's not enough, it's still 20% oxygen, but there's not even less of it there. You can't survive, at 20,000 feet. So we have to have the appropriate pressure, because we have to have enough oxygen molecules available so that we can suck them in and they can enter into our blood. Okay. I think I just said all that. Okay. And I think I just said all that. Yeah, 760 millimeters of mercury at sea level, but every 10,000 feet it gets cut in half. Now, okay, here's a term that you are going to be really, really, really tired of hearing me say. It's called homeostasis. Homeostasis means maintaining consistency. It means maintaining stability. It's the status quo. It is, everything is where it's supposed to be temperature-wise. We're at 98.6. Our blood pressure is 120/80. Our heart rate is 70 beats a minute. Our respiratory rate's 15 beats a minute. Our blood sugar is below 100, if you will. And everything is fine. Everything is in equilibrium. Everything is in balance. All the organ systems are working just fine. Our body desires to stay in homeostasis. And for the most part, it does. If we maintain a constant temperature, our breathing rate is pretty much the same. Our heart rate is about the same most of the time. We have fluctuations when we're doing something, but we like to stay in homeostasis. To do this, our bodies use something known as negative feedback. Our bodies have a whole series of functions designed to maintain homeostasis using this mechanism called negative feedback. Now, for negative feedback to work, you got to have three things. You got to have a sensor that is monitoring temperature and water levels and salt levels and oxygen levels and sugar levels in our blood. So we have a sensor, temperature. I think I said temperature anyway. So we have a sensor that monitors temperature. We have temperature receptors in our skin. We have temperature receptors embedded in the various organs in our body. They will monitor the temperature and they will respond if the temperature goes up or goes down. Now they don't do anything, they can't do anything themselves. The sensor is only designed to detect something, but it can send a signal to our central nervous system, our brain and spinal cord, and tell us, hey, I'm getting hot, or I'm getting cold. Or maybe it's another sense that says, I'm thirsty, or I gotta pee, or I'm hungry, or something like that. The central nervous system, the control center, receives a signal, and the central nervous system tells us what it is and decides that we're out of balance. We're too hot. And it decides what to do. So the control center will send a signal out to an effector. So if the sensor detects that you are too warm, the central nervous system will say, hey, we're too warm. We need to do something. And it will send a signal out to the sweat glands and make you sweat. Because what do you do when you get hot? You sweat, and you sweat to cool down. And you'll continue to sweat until, or I should say, you will continue to perspire. That's the technical term. You're going to continue to sweat until your body temperature or your skin temperature comes back to where it belongs. Because you don't, once you start perspiring, you don't continue to perspire, the rest of the day or whatever. You perspire until you've cooled down. And we're not aware of it. We don't. The beauty of this negative feedback is we don't think about it. We're not aware of it going on. We just, may discover, oh your clothes are sticking to your skin and your sweat's pouring off your head. But it wasn't like, oh, I'm getting warm. I better start sweating. It doesn't work that way. It's all automatic. And that's what homeostasis is all about. So this is what happens. The stimulus on the top there, the stimulus will act on the sensor. Perhaps it's, you've gotten warm. The sensor will send the signal to the control center, which will say, oh, I know what to do. And then the control center will send a signal to the effector. In the case of getting too warm, it would be the sweat glands. And then we will start perspiring and cooling us down until we get back to our normal temperature. See, this is the negative feedback loop. The negative feedback loop reverses the stimulus. That's why we call it negative. If you get too hot, the negative feedback loop cools us down. And once we get back to our regular temperature, we stop perspiring. So like you can see in the right-hand side there, the body temperature exceeds 37 degrees, which is normal body temperature. The sensory receptors detect that. They communicate to the control center in the brain. The brain activates the sweat glands and we perspire. And through the miracle of evaporative cooling, as water evaporates, it cools us down because it takes heat away with it. We bring our temperature back to 37 degrees Celsius and we stop. We stop being hot and we stop perspiring. Our body uses mostly negative feedback loops for everything. Whenever we get out of balance, whenever we end up in a condition of, let's just say, unhomeostasis, whenever we're out of homeostasis, whenever we're out of balance on some particular set point, temperature, salt level in our body, blood pressure, heart rate, things like this, whenever we're out of balance, our bodies will use a negative feedback loop to try to correct that, to reduce the original stimulus. A classic one is blood sugar levels. If you eat something, if you had something with carbohydrates in it this morning, if you had a bowl of cereal, if you had a donut, if you had an apple, whatever, the carbohydrates in that food are going to raise your blood sugar levels as they get, the carbohydrates are broken down into sugars. That's what carbohydrates are, they're sugars. And our blood sugar goes up, and we have a sensor that detects an increase in blood sugar, tells the central nervous system, hey, blood sugar's up. Central nervous system tells the pancreas, sits right here, to generate some insulin. We've all heard of insulin, right? Everybody knows insulin. Insulin allows the cells to take in that sugar. Because what it does is insulin tells the cells in our bodies to open up channels, little tubes in the cell membrane to let the sugar come in. And that whole process takes about 10 to 15 minutes from the time you eat something to the time the sugar gets. So that's how we get sugar in the cells. We use sugar as our source of energy. Glucose, the sugar I'm talking about, is our source of energy. And so we open up the cells, the sugar goes in, and we have power. And once we get our blood sugar levels back to where they belong, we stop releasing insulin, and everybody's happy. We got the sugar, we use the insulin, we got the sugar, the cells are happy, they're busy doing cell things, and we're ready for the next occurrence. So it's only when we get into problems where we can't get the sugar into the cell that there are some real difficulties. Do you have a question?
Yeah.
Okay.
So what happens when something the body does, like the sweating, causes another part of the system to go out of homeostasis? Like, for example, in the desert region, you sweat and you eventually dehydrate. You can't find water. What does it do?
Well, that's it doesn't end well. Bottom line, it doesn't end well. See, the opposite of negative feedback, I'm glad you brought this up, is positive feedback. Positive feedback enhances the stimulus. So like if you are hot because you're in the desert and you're sweating, the consequences of that, yes, you're going to cool down, but you're never going to cool down enough, but you're going to be losing so much water that you become dehydrated. And then if that process continues, it accelerates. The more water, the more water you lose through perspiration, the more dehydrated you become, and it amplifies itself. And then, if you don't have water to replace, then you're going to die.
So in other words, it doesn't stop; it just goes faster. Essentially.
Right. Essentially, it goes faster. The same thing happens with hypothermia. If you get too cold, if you get cold and wet, your body will start shivering to warm up, but you will shiver so much that you will perspire, and you'll become cold and wet again, and you'll have to shiver even more to try and warm up, and you'll start depleting all your energy reserves. When people hear the term hypothermia, they think of somebody, freezing to death in a snowbank or something like that. Hypothermia kills people when the air temperature is about 50 degrees if they've gotten cold and wet, because our body just continues to try and keep them warm, but goes overboard. You warm up, but then you perspire, and then you get cold again. In the desert, you're going to perspire, and you're going to lose all that water. And then if you can't replace that water, it's just going to get worse and worse. So there's only a couple of occasions where positive feedback in our bodies is a good thing. Childbirth is a positive feedback mechanism. When the baby is pressing up against the cervix is, now remember, in childbirth, the baby changes its position around so it's head down in the uterus, and the cervix is the opening from the uterus into the vagina. So the baby's pressing its head up against the cervix. That triggers the release of a chemical known as oxytocin. You'll hear all about oxytocin in AP2, probably more than you ever want to know. But oxytocin stimulates uterine contractions. And so you have that first batch of uterine contractions, and that causes the release of more oxytocin, giving you even stronger contractions, leading to more oxytocin being released and even stronger contractions. So you continue to amplify the contractions until the baby and the placenta are delivered. Positive feedback mechanism there, it works. It's one of the few places where we see it working. So, because most of our body is negative feedback to try and reverse the stimulus. Unfortunately, we end up, depending on the circumstances, we can end up in a very bad situation like that. So good point. Thank you for bringing that up. Insulin, and the point I was making about insulin is if the insulin, in our bodies, insulin is very important to us. Insulin opens up the cells to let glucose come in. But what happens if the insulin isn't recognized? If the cells don't recognize the insulin, then we can't get the sugar into the cell, and the sugar stays in our blood. Type 2 diabetes, you've all heard of diabetes mellitus. Our grandparents probably called it sugar diabetes. Anybody ever hear that term, sugar diabetes? Yeah. So it's still around. That's still the term that was used because it deals with glucose, and it's easier to say sugar than it is to say glucose. If adult onset diabetes, type 2 diabetes, which is the bulk of the cases of diabetes around the world and in the US, we're making insulin, but it's not being recognized. So we're not opening up the cells, and the sugar levels continue to rise and rise and rise. The other type of diabetes, type 1, what we would refer to as juvenile diabetes, we're just not making enough insulin at all. So that's that we're out of homeostasis on the insulin levels. Either it's not working or it's not there, and that means we're out of homeostasis on our blood sugar levels. Our blood sugar levels are skyrocketing, and on top of all that, your patient's starving, because if they're not getting sugar in their cells, they're not getting any energy. So there's a whole lot of things that happen at this point your patient's in a real world of hurt at that point when their blood sugar levels are way high, and yet they're starving too. So you'll hear all about that in AP2. Okay. So here's our little loop we have for negative feedback. It works both ways. If our blood sugar is low, we will release glucagon, a chemical also from the pancreas, which tells the liver to release glucose to bring our glucose levels back up. You can see the bottom part of the loop there. We want to stay around 90, have a glucose level around 90 milligrams per 100 mils of blood. To be consistent, just say 90. If you ever had blood work done, and you come back and then you say, oh, there's my blood glucose level, it's 87, and my doctor's happy. Or as long as it's below 100, your doctor's usually going to be happy. Anyway, but you were in a hurry today, you didn't have a chance to eat anything, and your blood glucose level drops. So your set point, you drop below your set point of 90. And your sensor tells the central nervous system, hey, my blood glucose is low, my blood sugar is low. And the brain says, okay, fine, and tells the pancreas not to make insulin, but to make the counterpart to insulin called glucagon, which tells the liver to release glucose, release sugar. Your blood sugar comes back up and you're happy. and you only release enough to get your blood sugar back up to normal, to your homeostatic point. On the other side of it is if we eat too much or have too much glucose, or I shouldn't even say that, when we eat something with sugar in it, our blood sugar goes up, tell the brain tells the pancreas releases insulin, and that sugar gets sucked up into the cells, and our blood sugar level drops back to normal. So both of these are negative feedback loops. Nearly everything we do in our body is negative feedback. Okay. And as I said at the end of the discussion about positive feedback, if negative feedback reverses the stimulus, positive feedback enhances the stimulus and makes it build upon itself. And childbirth is one of the few locations in the body, or few events in the body, where a positive loop is a good thing. Blood clotting is another one. We will, if we're bleeding out somewhere, we will generate a blood clot. We will make more and more clots form at the site of the injury to stop the bleeding, and that will continue. The positive response is to keep building a plug to stop the blood coming out. So that's a positive. That's the other positive feedback loop that works for our bodies. And oh, good question. Diabetic ketoacidosis. What happens? What about diabetic ketoacidosis in a diabetic patient? And that is a very, I'm glad you asked that. It's a very dangerous situation here. And I sort of led up to it. When your diabetic patient can't get sugar into the cells are starving. So the blood sugar levels rise because it's not going anywhere. It's not going into the cells like it should. You've got a patient and your blood sugar is supposed to be under 100, and you have a patient with a blood sugar of 600, but it's because it's not going into the cells. The cells are starving, and what the cells will start doing is they will start breaking down our body's fats. They'll start breaking down our body's fats to try, because you can convert fat to sugar. You can convert protein to sugar, but fat's usually what we go after. And the problem with that is that, I mean, it works because fats are made up of what we call fatty acids, so they can be converted into glucose. But as you process the fats, because the cells are starving, the cells don't know that the glucose isn't coming in. They just think that they're hungry. That's all the cell could, if the cell could think, it would say, I'm hungry, I want some glucose. So to start breaking down the fats, and the fats, when they get processed, release a chemical known as a ketone. Now, a ketone, if anybody's ever seen, used, or heard of fingernail polish remover. Fingernail polish remover is made up of something called acetone. And it is, has a very pleasant odor. Acetone itself is used all the time in chemistry, particularly in organic chemistry. But what will happen is our body will start producing high levels of these ketones. Now, your patient in ketoacidosis is now in a real world of hurt, because those acids, those fatty acids that they're breaking down to ketones, are driving their blood pH level down. Our body, pH is a measure of acid and bases. Our blood pH stands around 7.4. pH scale goes from 0 to 14. We like to stay right around 7.4. Well, we start adding in these acids, these fatty acids, as we're breaking down the fats. It starts driving our blood pH down more and more acidic. Now our bodies, and now this is where another system kicks in here. Our bodies are really peculiar. When we breathe out, well, let me rephrase that. When we suck in air, we use that oxygen to release energy. We also produce carbon dioxide. Carbon dioxide goes into solution in our blood and becomes carbonic acid, and that makes our blood slightly more acidic. Now, there's a point to all this. Anybody know what gas controls our breathing rate? Do we breathe faster because we need more oxygen? When you exercise and you breathe faster, why are you breathing faster? Thank you. Carbon dioxide. The faster we burn up sugar, the more carbon dioxide we release in our bodies. Carbon dioxide goes into solution, becomes carbonic acid. Our brain picks up that change in the increased levels of acidity and makes us breathe faster to blow off the CO2. We only exercise when we only breathe faster, not to get more oxygen, because we got a boatload of oxygen in our blood. We got plenty of oxygen in our blood. We only breathe faster to blow off the CO2. It always happens when your blood pH, you become more and more acidic. Well, guess what? In diabetic ketoacidosis, you got a patient who shows up breathing rapidly, breathing very rapidly because the acid level in their blood is, their blood is becoming more and more acidic. Their brain thinks, oh, well, we've been exercising. We've just been running a marathon. We better breathe faster because our pH is really low. We're very acidic. Only that's not the case. So your patient is breathing rapidly. Their blood glucose is around 600. And the big giveaway with ketoacidosis is they smell like fingernail polish remover because they're breathing out ketones. Ketoacidosis. It's the culmination of a whole series of events that get out of balance. Blood glucose levels alter, acid levels alter. The brain thinks one thing, because the brain doesn't know. All the brain can pick up on is the change in the acid level. Until there you are trying to figure out what's wrong with your patient, who their skin's dry and warm, and they're breathing rapidly. And they should be, if they've been exercising, their skin they should have perspiration, but it's not. And they smell like fingernail polish remover. Yeah, a lot of subtle situations there. Diabetic ketoacidosis is one of those life-threatening emergencies that you may never encounter, but because a whole bunch of things have to go wrong. So, yes, same thing with hyperventilation. You see a change in the, as it says here, fingers and limbs draw up because they're not blowing off enough carbon dioxide. Yeah. We'll spend a whole lot of time in AP2 talking about all the things that go wrong in diabetes, because it's one of the big, we're like in the top 10 in the country in Tennessee for diabetes. So it is the #1 endocrine problem around the world too. Thank you for those comments. That was good. So, okay, so I went down a big rabbit hole there. So let's, okay. Positive feedback loop, I already mentioned. There's what I was telling you about. The baby's head is tilted down, and you see that the cervix is this structure right here. It's a little tube that connects to the vagina, and it's the pressure of the baby's head on the cervix that causes the release of this oxytocin. So, okay. The problem with getting out of balance is as we age, it gets harder and harder to stay in balance. It's harder and harder to get us back into balance. When we upset our homeostatic balance and we don't fix it, we increase the chance of some sort of pathological condition, some sort of disease. A person who starts to develop elevated blood pressure. Some patients are going to start, you're going to start seeing a rise in their blood pressure, maybe in their mid-30s, and it'll start climbing each year a little bit. It usually takes if you're seeing a patient year after year, and you start seeing a gradual rise in their blood pressure, because it's usually not going to jump like from 120/80 to 180/100, in 1 year, usually. But there's going to be a gradual increase. So now your patient is suffering from hypertension. They're seeing this gradual increase. Hypertension is one of the easiest conditions to control. If it's caught very early. Blood pressure medication, hypertensive blood pressure medication is inexpensive and easy to take. One little pill a day for your patient. The problem with hypertension is that it doesn't have any real overt symptoms for about 30 years. So if you have a patient that starts developing uncontrolled elevated blood pressure at 30, and they don't follow the directions to take one little pill every day, by the time they're 60, they're dealing with kidney damage and heart disease and risk of stroke, all because of the higher pressure, higher blood pressure. Increased, they have a greater risk of having their quality of life diminish and have premature death simply because of this onset of hypertension. Other things happen as people age. We tend to wear out a little bit. You may discover patients that never wore glasses until they turned 40. About a person who never had to wear glasses, that didn't have myopia, they weren't nearsighted early on. Kids start wearing glasses, early because they develop myopia early. But that's nearsightedness. Farsightedness doesn't tend to show up in adults until they're about 40 years of age. And so what do? You start wearing glasses or contacts. If you have myopia, if you're nearsighted, you have laser surgery at some point to fix it. Your eyes become less efficient. You have difficulty seeing unless you have corrective lenses. So it's a very common occurrence in adults that didn't have any kind of eyeball condition earlier, tend to start becoming farsighted at around the age of 40. It's because the shape of the lens changes. It's no longer in equilibrium. It's no longer in homeostasis. And you do things, your patient will do things to accommodate this. They'll try to read something like this and they'll discover, oh, I can't read it here. I got to move it out to here to see it. Have you ever seen anybody do that? Yeah. It's simply because it really is very simple why you do that. Because when you do that, you move the image in focus on your retina. That's all it does. When you're holding something out like that, the light rays are now focusing on your retina. When it's up close like this, and your patient is farsighted, the focal point, the point where the light rays coming off this would be visible, is actually behind the retina. Now they can't get there because the retina is solid, but it's not in focus. So you pull it out like that. It's one of the first signs that your patient's developing farsightedness. Yeah.
I just have a question. I know that people develop milk allergies later in life, and I wonder if that had something to do with aging, or if that's just.
Oh yeah, a lot of us that drank a lot of milk when we were kids don't drink it now because it doesn't agree with us. I still love ice cream, but ice cream doesn't like me anymore. So it's rare that I eat ice cream, which is a real shame. But
I'm the same way. That's why I was curious. I used to drink milk all the time, but now I can't hardly drink milk.
yeah, as we age, our ability to process the sugar, the lactose, the milk sugar in there, it seems to break down more frequently or not break down properly. So a little milk doesn't hurt, a lot of milk does. You know, the days of drinking a whole big glass of milk, they're gone. You know, that's part of the aging process. You know.
Can it be like that with other foods too?
Oh, yeah, yeah. Foods that we could eat plenty of or that we liked when we were young, don't agree with us now. You know, dairy products in particular, but there's other things too. You know,
I went like my whole life without like eating corn, rice, and sesame seed and milk. And then we come to find out my freshman year of high school, they were like, this is the reason you're sick, you're allergic to these foods. So I was just, it just makes sense now.
Oh, yeah, yeah, because, you know, our bodies can't process some of these things, or we lose the ability to process them later on in life. And, you know, because I know that corn, I love corn, but it doesn't love me anymore. So that's another thing. And I appreciate that one completely too. So anybody else have any good allergy stories they want to share? So, or food stories? I mean, this is, you know, that's part of the aging process too. You know, as long as it doesn't mess with my coffee, I'll be happy. So, but you know, there are things that we seem to lose the ability to do things. I guess we had a lot more flexibility. Our digestive system had a lot more flexibility when we were younger than we are as we become adults and we start aging. You know, one thing I found is that I'm less sensitive to hot salsas now than I was when I was younger. So now you know, it has to have a real wallop before I think, oh, you know, that was hot these days. So anyway, okay. When our patients age, it does get, part of the aging process is it does get harder and harder to stay within equilibrium. And so you're dealing with a lot of little things that start accumulating. Heart disease is a real good example of this. We have a lot of heart disease in the South. We have a lot of heart disease in Tennessee. And part of it's diet, part of it is hereditary. You know, it's one of those that some people develop heart disease who do everything right, and some people develop heart disease who do everything wrong. People are peculiar. You're going to have a 95-year-old patient who knocks down biscuits and gravy and country steak every day, and their heart is the heart of a 20-year-old, and they're fine. You know, they're going to die because they got run over by a beer truck in front of the liquor store. You know, because they looked the wrong way. They don't have anything wrong with their heart. Their cholesterol levels are perfect. Their sugar levels are perfect. Everything's fine. You know, but they're the anomaly. You're going to have the 50-year-old who's done everything right and has heart disease. And then you're going to have the people that have the biscuits and gravy every day and the country fried steak and the high fat foods and the no exercise. And they're going to have various forms of heart disease, which is, again, still a pretty, you know, early onset, that's still a pretty fixable problem. But one thing leads to another. You develop, when the heart gets worn, you know, as the heart, the term heart disease and heart failure are sort of like a catch-all term. What happens when a person has a diet high in fat? The fat tends to accumulate inside their coronary arteries and reducing the flow of blood going through there. So it tends to clog up the arteries that supply the heart itself. What happens is, for the heart to continue to maintain the same amount of blood, it has to work harder. It has to pump more frequently and more vigorously to get the same amount of blood that it was getting before when the arteries were open. The heart doesn't like that. As the heart pumps more frequently, it will enlarge. Now, normally a muscle enlarges when it exercises a lot. And, if you're an athlete, yes, your heart will enlarge, but that's a good thing. It will get bigger and more powerful, but more efficient. An athlete who trains constantly may have a resting heart rate of 50 beats a minute. Normal heart rate is about 70 beats a minute, but they can have a perfectly fine heart rate of 50. Plenty of blood going out to their body at 50 beats a minute. Very powerful contractions. A person who doesn't exercise and has, okay, that was new. A person who doesn't exercise, who has high levels of plaque, we call this fatty deposit plaque in the arteries, reducing the flow of blood through there, the heart has to work harder. When it works harder, it gets bigger, but it doesn't get stronger. That's okay. That's the enlarged heart. An enlarged heart is not a good thing. As it gets bigger, it gets weaker, and it usually tends to be one side or the other, and that tends to lead to what we call heart failure. Heart failure is a way of describing, oh, they're doing sign, I know what they're doing now. So heart failure is when one side of the heart can't keep up with the other, and the blood, if the left side is supposed to send 100 mils of blood out to the body, 100 mils of blood better be coming back to the right side. What happens if only 50 mils comes back to the right side? That other 50 mils of blood gets backed up in the tissues and you get swelling and stuff like that. Yeah. Congestive heart failure ultimately leads to death. Yeah. I've seen on cadavers, I've seen an enlarged heart. Normally your heart's the size of your fist. I've seen one that was the size of a football in there. So it gets bigger, but it gets flabby. Heart failure is, it starts out slow. It doesn't happen overnight. It takes time to make the heart unhealthy. And you're out of balance there. Your patient is going to have unless they correct it, it's going to have a gradual occurrence here. And yes, cardiomegaly, a prior heart attack, the heart can be damaged. The heart becomes less efficient. We call it a heart attack. What happens with a heart attack is if we're blocking the arteries, in addition to the heart working as hard as it can work, sometimes we may block the artery completely. That's what a heart attack is. A heart attack is a blockage of an artery in the heart, and it starts killing tissue downstream of the blockage. So that's what we try to stop that as best we can. So, okay, now this is just, we've been talking a lot about glucose levels. These are examples of what we call PET scans. I think it's positive emission tomography. And we can track glucose use in the body using these PET scans because cancer cells tend to use more glucose than other cells do. And so we can look and see where the glucose levels are excessively high in the body to identify where a tumor or tumors has spread. And you can see here, for example, right up here I'll use this one. There's something there, Now this may or may not be something of value here. This may be part of the stomach. It may be the pancreas, but up here is something that shouldn't be there. And that could be a tumor. It's a very good way to detect the spread of various cancers. Okay, now, so let's try and crawl out of the rabbit holes. I forget how many rabbit holes we've got now, but that's okay.
Like 5.
Yeah, and they're interconnected too. So, okay, terms. Anatomical position. It's number one term. The anatomical position. This term is used all the time. And what it is if the body is standing upright, the palms are facing forward like this. Your thumbs are sticking out to the side. So if you were to have a patient in the anatomical position, they would be like this. Palms out, palms facing out, thumbs out. Whether they're on the operating table or the examining table, this is the anatomical position. Everybody is familiar with that position in healthcare. They know what it is. Now, it gives you a good frame of reference. That way you can use the anatomical position to look at, different locations on the body and not be confused. So I will tell you that one of the great distractors that you might see on an exam question about the anatomical position is the anatomical position. And, you have, the A, B, C, D, or E, and it says the anatomical position, the most comfortable position to use when dissecting a cadaver. Sounds good, but that's not it. So it is the standard of reference type of thing. I'm just sort of giving you an example that you may or may not encounter in the future. That's called a hint. So.
In other words, write it down.
Thank you. Yes, I didn't say that, but thank you. So, okay. So we base all of our directions off of the anatomical position. We don't use left and right as we see it. We use left and right of the body as it's laying there. So, and we tend not to use left and right too awful much anyway. The terms we use: anterior and posterior. Anterior is in the front, posterior is in the back. The other term that we use for anterior and posterior is ventral and dorsal. If you think of the dorsal fin on a shark, that's on the shark's back. So dorsal is the backside, the posterior. Anterior or ventral, I don't have a good reference for analogy for ventral, but anterior is front, posterior is back. Ventral is front, dorsal is back. Superior is above, inferior is below. Lateral and medial. Now we will use lateral and medial all the time. Imagine a midline, a line running right down the middle of the body. So that's the midline. Something that isn't medial is, anything medial is close to the midline. Anything lateral is away from the midline. Now I know it can be variable because different things are gonna, but if we're talking about the lateral side, we're looking at a bone and we're talking about a structure on the bone. And is that structure a lateral structure or a medial structure? If it's closer to the midline, it's always medial. If it's away from the midline, it's always lateral. And that'll make much more sense when we start looking at bones. Yeah.
Would that change with like comparison? So like if you're talking about like something being in the middle of the bone, but you're comparing it to like something on like say the interior of the right side, is that like?
Oh yeah, it's going to be variable depending on what, it all depends on your perspective, but if we're looking at a bone, for example, here on the end of the humerus, I can take it apart, but on the end of the humerus, there are two projections, one on either side. They're called epicondyles. You'll hear all about this in lab in a couple of weeks. The epicondyles, one is the medial epicondyle, one's the lateral epicondyle. One is on the outside of the bone, one's on the inside of the bone, medial and lateral epicondyles. So it has to do with the position. What's nice about some of these bones, these structures, is it doesn't matter which way you turn the bone around, it's still the same medial and lateral. So, but if you're looking at different locations within the bone, then yeah, it's going to be variable to you. So, okay, proximal and distal. Proximal closer to the source, distal away from it. So that's another one of those variable things where proximal and distal, we try to avoid using that too much. Superficial and deep. Deep within the tissue or on the surface. The terms we use the most are going to be anterior, posterior, superior, inferior, medial, and lateral. We use those more probably than anything else. And try to remember some of these as we go through the semester. A lot of these terms will become second nature to you as we go through them. So, now, when we look at our bodies, we can divide them up into a couple categories. We have two big divisions, the axial division and the appendicular division. The axial division is the part of the body lined up on the vertical axis. So it's the head, the neck, and the trunk. The skull, the vertebrae, for example, the ribs are all part of the axial division. The appendicular division is everything else. The arms and legs, hands and feet, fingers and toes, the shoulders, the hips, the knees. Those are all part of the appendicular division. And we separate these out, and then we have some regional. Some areas we focus on, specifically like the shoulder, what we call the shoulder girdle, and the pelvic girdle, the hip region, for example. Now, okay. Now this covers all the regional terms of the human body. Now, a lot of these you're going to hear over and over again. So don't look at it and say, how am I ever going to remember all this? But a lot of it is will become second nature to you as we go on. A lot of it you've already heard of. Who hasn't heard of the axillary region for the armpit? You have now. So what about the large bone in your thigh? What's that called? The femur. Okay, that's on the list here. What's the proper term for your butt? Gluteus maximus. Gluteus is on the list. Something as how about digits, phalanges? That's something pretty straightforward. Patella, your kneecap. Most of us have heard patella at that point. The hip bone. What about the abdomen? The thorax for the chest. The nasal region for the nose. The cervical region for the neck. So a lot of these terms you're going to become very familiar with over the next 2 semesters, but not all at once. So we're going to pick it up as we go along. So, but these are the terms that we'll become very familiar with as far as the regional areas of the human body. Some more than others. Some we'll talk about more than others, but yes. Okay, the body can be divided up for referencing in 3 distinct planes. We have what's known as the sagittal plane. A sagittal plane or a sagittal cut divides the body into a right and left side. Doesn't matter where we make a cut to divide it into the right and left. We try to, if we cut right through the body, like we see here, the sagittal plane would give you a right side and a left side. And it doesn't have to be in a straight line. It could be a cut that goes right through the elbow on the side, giving you everything on one side and just a little bit on the other side. It's still a sagittal cut. Any kind of vertical cut giving you a left and right side. That's a sagittal plane or a sagittal cut. A frontal cut gives you a front and back. So, or anterior and posterior. And it can be a cut that goes through the tip of the nose and leaves everything else that way, or it can be through the back of the skull and leave everything in front, doesn't matter. It gives you an anterior and a posterior. And then the transverse cut, which we still call a cross section, will usually give you a superior and inferior. So like if we're cutting our victim here in half, we have a top and a bottom, a superior and an inferior region. So sagittal, frontal, transverse. So sagittal plane, the sagittal cut gives you a left and right. If you cut right down the middle, it is called a mid-sagittal cut. Anything not down the middle of the body is a parasagittal. So it can be anywhere on either side off the midline.
Is that phrasing based off like parallel?
Yeah, yeah. So, because you're trying to make it, you're going to make a, if you consider the midline runs right down through the middle of the body, right down through the middle of the nose, anything on either side of that, a parallel line, parallel cut on either side of that gives you the parasagittal plane. Okay. Frontal cuts, coronal cuts, same thing. Gives you an anterior and a posterior. Transverse is the cross, is the cross section, and an oblique cut, which we don't see a lot of, is at an obtuse angle. Okay, so this is an MRI of a mid-sagittal cut. If you look at the bottom part of the picture, you can see full color MRI, and you can see where we have, in fact, you can see the vertebrae, the cut right through the vertebrae. You can see the rectum down at the bottom on the lower left of the picture, and the intestine sort of in the middle, right in front of the spinal column. Here we see this is a CT of a individual. Again, this is a mid-sagittal cut. We can see the vertebrae. You can see part of the shoulder right here. This, by the way, is a roofing nail that was inserted into an individual's heart when they were checking to see if their nail gun was loaded. They survived, by the way. I'll just let you know they survived. So the human heart is amazing. It's what the amount of trauma that the heart can take. But yes, yeah. So, but this is a mid-sagittal cut. You can see the usefulness of it right there, because before you want to go in and start doing surgery to take that object out of the heart, you got to know what you're looking at.
Explicitly positioning.
Oh yeah, yeah. See, now the beauty of a penetrating injury to the heart is the heart tends to close up around the penetrating object, so you don't go yanking it out.
No, you can't.
Right. Remember Steve Irwin, the crocodile hunter? He died because he had a stinger lodged in his heart, and being, he yanked it out. He may have survived if he hadn't done that, because he bled out from that. So, okay, I think on that note, we will stop here. This is always a good picture to stop on. And we will pick up on Monday. We'll finish this on Monday and start moving into chemistry. Okay, so lab this out, if you're in lab the rest of this week, we are looking at, we'll spend some time talking about the ground rules of the lab, and then I'll start talking about what we'll go over the parts of the microscope and what we call the epithelial cells. So, and then take us, see how far we get before we get bored. So, okay, I'm gonna get us out of here, and I will see you all later.